Okay, today let's have a look at lesson 4 of chapter 2, which is about applications of derivatives. So basically, we'll put what we have learned so far together to solve some real-world problems. Okay, let's first the learning goals of this lesson. So after this lesson, you are expected to apply derivatives to solve typical problems in business and economics, and apply derivative to solve typical problems in physics. Okay, first of all, let's have a look at the applications of derivatives in the domain of business and economics. Okay, so in this field, there are some functions you need to know. First is the demand function or price function, which is denoted usually by Px, where X is the number of units of product or service that can be sold at a particular price. That means the price is a function of the product number of products. Next, another very commonly used function is a revenue function, which is always denoted by Rx. Apparently, Rx is the product of X and Px, right? Unit price times the number of units of the product. Then we have the cost function, which is always denoted by Cx. Cx is also a function of X. X denotes the number of units that has been produced. Last, we have the profit function, P. And profit is defined as difference between your revenue and cost. So Px is the profit from the sale of X units of a product or service. The profit function is difference between the revenue function and the cost function. Therefore, we have Px equals Rx minus Cx. So the primary goal of most businesses is to generate profits. To achieve this goal, many different aspects of this business need to be considered and measured. For instance, a business has to determine the price for its products that will maximize the profits. If the price of a product or service is set too high, fewer consumers are willing to buy it. This often results in lower revenues and lower profits. If the price is set too low, the cost of producing large quantities of the item may also result in reduced profits. A delicate balance often exists between the cost, revenue, profit, and demand functions. Okay, so you need to be careful here. In the field of economics, in convention for demand or price function, the price is taken on vertical axis, and the quantity X is taken on horizontal axis, and express P as a function of X. Probably this is not very intuitive, but this is by convention, okay? So just put Px on the vertical axis and your X on the horizontal axis. You understand? Well, although you might think the demand is dependent on price, right? So the independent variable should be the price. But by convention, we put the price Px on the vertical axis, not the horizontal axis, okay? This is just in convention, so be careful with this. You understand? Okay, then let's have a look at the derivatives of business functions. So economists usually use the word marginal to indicate the derivative of a business function. For example, the derivative of cost function with respect to X, dc by dx, is a marginal cost function and refers to the instantaneous rate of change of total cost with respect to the number of items produced. R prime X, or dr by dx, is called marginal revenue function and refers to the instantaneous rate of change of the total revenue with respect to the number of items sold. P prime X, or dp by dx, is the marginal profit function and refers to the instantaneous rate of change of the total profit with respect to the number of items sold. Okay, so these are some basic concepts in the domain of business and economics. So note we have 3 or 4 types of important functions, okay? Demand function or price function, revenue function, cost function, and profit function. So next, let's have a look at a specific example to illustrate the important concepts here. So consider this question. A company sells 1,500 movie DVDs per month at $10 each. Market research has shown that sales will decrease by 125 DVDs per month for each 0.25 increase in price. So there are 5 questions. A, determines the demand or price function. B, determines the marginal revenue when sales are 1,000 DVDs per month. C, the cost of producing X DVDs is given by this function. Determines the marginal cost when the production is 1,000 DVDs per month. Button D determines the actual cost of producing the 1,001 DVD. And question E determines the profit and marginal profit from the monthly sales of 1,000 DVDs. Okay, I'll give you 5 minutes to have a look at this question by yourself, okay? Okay, have you finished? Okay, so let's have a look at the solution together, okay? You are already familiar with this question. So let's have a look at the solution. First, we want to determine the function of P with respect to X, right? So we can let P be the price of one movie DVD. That's a unit price. Then let X be the number of DVDs sold per month. Then let a variable N be the number of $0.25 increases in price. So we have the following two equations derived from the given information. First of all, X equals 1,500 minus 125N, right? Can you see why? Because it says the sales will decrease by 125 for each $0.25 increase in price. Therefore, if you let N be the number of 0.25 increases in price, then the number of DVDs can be sold is 1,500 minus 125N, right? Not difficult to understand, right? So next, the price will be the original price 10 plus 0.25 times N, because N denotes the number of the price increase. Remember, we want to establish the connection between P and X, right? We want to find the function of P in terms of X. So from equation number 1, we have N equals 1,500 minus X over 125. So we can substitute this expression into equation number 2. Okay, I'll enlarge this a little bit. Okay, if you substitute this expression into number 2, this will give us the function of P in terms of X, which is P equals 10 plus 0.25 times 1,500 minus X over 125. So we can simplify that expression. Therefore, P equals 13 minus 0.002X. So that's a function of P in terms of X, right? Which is called the price function or demand function. And actually, this function gives the price for one DVD, one X of them are being sold. Okay, so just note here, this is our demand or price function, PX. Any questions? Okay, so that answers the first question. Next, let's have a look at the revenue function. Remember, the revenue function Rx is a product of PX and X, right? Unit price times the number of units sold. So here we have already known the PX. So PX is 13 minus 0.002X times X. That gives us a revenue function, which is Rx equals 13x minus 0.002x squared. Then in order to find the marginal revenue, you need to take the derivative, which means R prime X or dr by dx is 13 minus 0.004x. And note here, we want to find the marginal revenue when X equals 1,000, right? So put 1,000 into that equation. We find R prime at 1,000 equals 13 minus 0.4 times 1,000, which gives us 9. So this means when sales are at 1,000 DVDs per month, revenue is increasing at the rate of $9 per additional DVD. Any questions? No? Okay, then let's see question 3. Question 3, we want to find the cost function CX. Sorry, the cost function CX is given to us, right? Therefore, question asks us to determine the marginal cost. Therefore, we need to differentiate CX with respect to X. So C prime X is negative 0.008X plus 9.2, right? Again, we want to find the marginal cost at X equals 1,000. So just plug 1,000 into that equation. C prime at X equals 1,000 equals 1.20. So this means when the production is at 1,000 DVDs per month, the marginal cost is $1.20. Okay, next question. The cost of producing the 1,000 first DVDs is, you can calculate this using the difference of producing 1,001 DVDs and the cost of producing 1,000 DVDs, right? So we can just plug 1,001 into CX and 1,000 into CX as well. The difference will be the cost of producing the 1,000 first DVD, which gives us $1.196. So as you can see here, the actual cost of producing the 1,000 first DVD is $1.196. Notice the similarity between the marginal cost of the 1,000th DVD and the actual cost of producing the 1,000 first DVD. For large values of X, the marginal cost when producing X items is approximately equal to the cost of producing one more item, the X plus 1 item. Okay, next one. The profit function is given by profit X Px equals Rx minus Cx. So be careful with the notation here, okay? For profit function, usually we'll use uppercase P, standing for profit. The lowercase px, standing for price of X. Price in terms of X, okay? So profit is given by uppercase P in terms of X, which is the revenue minus the cost. Because we have already known the expression of Rx and Cx is given to us, we can just plug them in. Then the profit function in terms of X is simplified to 0.002 X squared plus 3.88 X minus 5,000. Then we can calculate the profit at X equals 1,000. Just plug 1,000 in. This gives us P1000 equals 800. And also we want to find the marginal profit when X equals 1,000, right? So first of all, differentiate Px to get the marginal cost at any X. P prime X is given by 0.004X plus 3.8. Therefore, the marginal profit at X equals 1,000 equals 0.004 times 1,000 plus 3.8, which equals 7.80. So that means when 1,000 DVDs per month are sold, the total profit is $800, and the marginal profit is 7.80 per DVD. You understand? So make sure you can solve each of the each of the questions here. Okay. So this is it. This example illustrates the key concept in the domain of businesses and economics. Do you have any questions? No? Okay, then let's have a look at another example in the business and economics domain. So this time, we have a ice cream shop sells 150 cookies and cream ice cream cakes per month at a price of $40 each. A customer survey indicates that for each $1 decrease in price, sales will increase by 5 cakes. First, determine a revenue function based on the number of price decrease. B, determines the marginal revenue for the revenue function developed in part A. C, what is this marginal revenue function equal to 0? What is the total revenue at this time? How can the owners use this information? Okay, I'll give you 5 minutes to have a look at this question by yourself. Okay. Okay, have you finished? Okay, let's have a look at the solution together. First, remember it is just it is not always necessary to involve the demand function as in previous example, right? Sometimes you don't have to find the price function or demand function. Just note that revenue equals price times sales, right? So if we let n represent the number of $1 decrease in the cake price, then the price would be 40 minus n, right? So for each decrease in price, cake sales increase by 5. So the sales of the cakes is 150 plus 5n. So we can express the revenue function Rn as 40 minus n times 150 plus 5n without explicitly finding the price function, right? So we just express the revenue function in terms of n. N represents the number of $1 decreases in the cake price. Okay, next one, we want to find the marginal revenue. So marginal revenue is just derivative of Rn, which can be calculated to negative 10n plus 50. Then we can solve R prime n equals 0. Solve this equation, gives us n equals 5. That means the marginal revenue is 0 when there are 5 $1 decreases in the price of the cakes. Cakes then sell for $35, right? So we can find the revenue at n equals 5 as well. So the revenue when n equals 5 is 40 minus 5 times 150 plus 5 times 5, which gives us 61.25. So that means when the price is $35, the total revenue is 61.25. Okay, so how the owners can make use of this information? The interpretation of this information is as follows. So note here, the revenue function is a quadratic function whose graph is a parabola opening downwards, right? At the point where the derivative or the marginal revenue is 0, the revenue reaches its maximum value, which is at its vertex. After this point, as n increases, the unit price P decreases, the total sales increase, but the total revenue will decrease. So we can find the optimum value for n to maximize our revenue, right? This is a useful information for the owner of this business. Okay, any questions? Okay, if you have no questions, let's see the second aspect of today's lesson, which is the applications of derivatives in physics. Okay, so let's have a look at this example here. Apply derivatives to kinetic energy. Kinetic energy K is the energy due to motion in physics. When an object is moving, its kinetic energy is determined by the formula K equals 0.5 mv squared, where K is in joules. M is the mass of the object in kilograms, and v is the velocity of the object in meters per second. So suppose we have a ball with a mass of 350 grams, is shown vertically upward with an initial velocity of 40 meters per second. Its velocity function is vt equals 40 minus 9.8 t, where t is time in seconds. There are two questions. First, express the kinetic energy of the ball as a function of time. B, determine the rate of change of the kinetic energy of the ball at 3 seconds. Okay, I'll give you 5 minutes to have a look at this question And then we'll have a look at the solution together, okay? You can start now. Okay, have you finished? All right, let's see the solution together. First, question A, we can substitute m equals 0.0340 kilograms and Vt equals 40 minus 0.9 T into the kinetic energy function. Kv equals 0.5 mv squared, right? So the function of the kinetic energy of this object is given by kt equals 0.175 times 40 minus 9.8 T to the power of 2. In order to find this rate of change of the kinetic energy at any time, we need to differentiate kt, right? So the derivative of k with respect to t, or dk by dt, is negative 3.43 times 40 minus 9.8 T. So be careful here. If you differentiate kt, we need to use the chain rule here, okay? So next we can find the instantaneous rate of change of the kinetic energy at t equals 3. So just insert t equals 3 to the derivative of k. That'll give us k prime at t equals 3 equals negative 36.358. So that means at 3 seconds, the rate of change of the kinetic energy of the ball is negative 36.358 joules per second. The negative value indicates that the kinetic energy is decreasing. Any questions? No? Okay. If you have no questions, let's see another example. In physics, apply derivatives to electrical currents. In a certain electrical circuit, the resistance R in ohms is represented by the function R equals 150 over I, where I is the current in amperes. Determine the rate of change of the resistance with respect to the current when the current is 10A. Okay, I'll give you 3 minutes to have a look at this question by yourself. Okay, have you finished? Okay, let's have a look at the solution. Okay, first of all, R equals 150 over I, right? Which is 150 times I to the power of -1. Therefore, we can find the derivative of R with respect to I, which is -1 times 150 times I to the power of -2. Then dr by di at I equals 10 equals 150, -150 over 10 to the power of 2, right? That gives us -1.5. So that means when the current is 10A, the rate of decrease of the resistance is 1.5 ohm per amps. You have any questions? No? Okay, you don't have any questions. Let's have a look at another concept in physics, which is about the mass function, average linear density, and linear density. So first of all, let's have a look at the concept. Suppose the function fx gives a mass in kilograms of the first x meters of the object. For the part of the object that lies between x equals x1 and x equals x2, the average linear density or mass per unit length is defined as the difference between fx over the difference between x, which means fx2 minus fx1 over x2 minus x1. The corresponding derivative function dfx by dx is called the linear density at any point x. So this is a concept of linear density. For example, let's have a look at the three diagrams here. The mass function is m equals fx, right? This gives the mass of a object of the first x meters of the object, m equals fx. And then we can find the average linear density from x1 to x2. This is given by the difference between the masses over the difference between the x, the length, right? Which is fx2 minus fx1 over x2 minus x1. So the derivative of the density of the mass function dm by dx is actually the linear density at any point x. This is by definition. Okay, so be careful with the concept linear density. What does this mean? This means the derivative of m with respect to x. So note here, the linear density might be different along the length of the object, right? It could be different at any point x. Okay, so let's have a look at an example to illustrate these concepts. First, the mass in kilograms of the first x meters of a wire is represented by the function here, fx equals square root of 3x plus 1. There are two questions. A, determine the average linear density of the part of the wire from x equals 5 to x equals 8. Next, determine the linear density at x equals 5 and at x equals 8. Compare the densities at the 2 points. What do these values confirm about the wire? Okay, again, I'll give you 5 minutes to have a look at the question first. You can start now. All right, have you finished to find the result? Okay, let's have a look at the solution together. Okay, first of all, according to the definition, average linear density is defined as delta F over delta X, right? So we can simply put F8 minus F5 over 8 minus 5. So that gives us the average linear density between 5 to 8 is 0.33. So the average linear density for this part of the wire is approximately 0.33 kilograms per meter. So next, in order to find this linear density at some point x, we need to differentiate fx, right? So the linear density at any point x is defined as df by dx, which is given by 1 over 2 times 3x plus 1 raised to the power of negative 1/2 times 3. Also note here, if you want to differentiate fx, you need to use the chain rule here, okay? The outer function is 3x plus 1 to the power of 1 over 2. The inner function is 3x plus 1. Remember to use the chain rule here, okay? Then in order to find row 5, simply put x equals 5 to f prime x, which get us 0.375. And the density at x equals 8, you can just insert x equals 8 to the linear density function. This gives us rho 8 equals 0.3. Therefore, the conclusion is the linear density at x equals 5 is 0.375 kilograms per meter. And x equals 8, at x equals 8, it is 0.3 kilograms per meter. Since the two density values are different, they confirm that the material of which the wire is composed is non-homogeneous. Any questions? Okay, so that's the last example of today's lesson. So before we end today's lesson, let's make a short summary. So today, after today's lesson, now you should be able to apply derivatives to solve typical problems in business and economics, as well as in the domain of physics. Okay, so we have seen 5 examples today. I hope you are able to solve similar questions as these one. Okay, any questions? All right, if you don't have any questions, class dismissed. I'll see you next time.